Exciting to be here, and I've been waiting for 2:30 to really give this talk. I hope you guys hear me well. Okay, awesome. I really want to stimulate some discussion around the type of work we've been doing over the past couple of years. And I really appreciate the opportunity to present this work in the connection between space travel, space flight, and space biology and longevity. A little bit about myself. I'm a founder of the Stanford 1000 Immunomes project. 15 years ago, I've been with Stanford. Only 3 years ago, I got appointed at the Buck Institute for Research on Aging to lead the AI platform Bioinformatics 4. And as part of the Stanford 1000 Immunomes, we were pioneering really the use of multiomics in the immune system. And that's my focus, is how the immune system determines rates of aging in different organs and systems. And we actually have a diagnostic test for anti-aging that was the foundation of the creation of this company, Edifice Health, that has been funded and now is taking a life of its own. But today I'm going to talk about something different. I don't have to convince you guys that the rates of aging or the older population is growing. Humanity is facing a big problem. And that is that within the aging population, there's also an increase in the rates of chronic disease. We're getting sick, and that's a big problem. That's exemplified by the fact that we're spending over $3.5 trillion annually, only in the US, in expenditures in healthcare due to chronic disease. So if we don't find cures for aging, the whole healthcare system will collapse. So I think everybody also knows this picture here, that traditional drug discovery and development is pretty slow and expensive. Right? And one of the reasons that we think that's the case is because of the well-described gap between animal models, other model organisms, and humans. And most of the research that has been done in aging and longevity and the hallmarks of aging and everything else has been based on worms, yeast, flies, and maybe mice, right? We're not using any of that. And I think that becomes a big issue in the drug industry because things don't translate. Just as an example, a master regulator of the immune system, gene called MX1, doesn't even exist in mice. Mice don't even get the flu. So it's very different from what happens in humans. At the same time, very interesting, the space industry, everybody knows, is growing, and the private sector is taking over with SpaceX, Axiom, Blue Origin, and this creates a really incredible opportunities. And that is because we really want to go in deep space, right? Elon Musk is saying maybe we'll go and land in Mars in 2024. I find this a little bit probably not realistic, but NASA is expecting to land in Mars in 2030. This causes some challenges. The whole space industry has been dominated by engineers for the past 70 years. And we believe if we send a rocket and it's out of space, we're good. That's not what's happening, and that's not going to will take us ultimately to Mars or deep space. It is inevitable that we will become an interplanetary species, but there are several challenges when it comes to human biology, humans in space, and that is mostly aging, accelerated aging. Okay, so what I'm showing you here is a summary of multiple studies that have been done in crew members that suffer from cognition decline in accelerated cardiovascular issues, such as altered stiffening of the arteries, obviously bone loss, muscle loss, also declining metabolic rate. This is what happens in normal aging. The dashed white line here. In say 80 years or 100 years of life. And this is what happens during space. Much accelerated, 30-fold. So there's a window, right? Say 6 months or a year, where these individuals are in the International Space Station for us to gather data and look at aging at an accelerated fashion. And I'm very excited about this. That's why I'm here. I think I've been waiting so long for this talk. I think I will claim that this is the first human non-disease. This is not progeria model. This is not Down syndrome, right? For human aging. Also, because the space industry is growing so fast, now we're doing experiments in space. We have Inspiration 4, we have Axiom 2, Axiom 3, that's going to come pretty soon next year, where we collect multiomics before, during, and after spaceflight. And so we've had this very unique opportunity to study aging at an altered rate in humans. And here's where I would like to introduce this company that we founded very recently. It's called Cosmica, Biosciences, and it's really sitting in this overlap between spaceflight pathology and normal aging on the ground. Yeah, so some of the team members of Cosmica, my co-founder, Chris Mason, he's been a PI of around 5 to 10 missions, NASA missions, SpaceX, Axiom, etc. And so we have a very good tie to Cornell, and we're licensing data from them. And we get all this data alongside with ground analogs of microgravity and as well as galactic radiation. I'll show you some of that. My other co-founder, Don Weiner, he's an expert in mechanobiology and immunometabolism. And other team members of the group here, all trained with us PIs here. And overall, scientific advisory board, I think we have over 150 years of in total, right? When you sum up all the experience that these folks are bringing to the story field, between Eric Antonsen at NASA and Baylor, John Manik, Gene Wong. We're talking about drug discovery, drug development, data science, and aging combined over 150 years of experience here. So let me introduce you to the platform that we built. We call that Pronto. And it goes for platform for rapid output of novel therapeutics using RNAs. The first thing we do, and the promise really, is that we can reduce the very first part of drug discovery, including target validation, compound screening, and maybe lead optimization by 15-fold. Because we have this model of accelerated aging, we can determine biomarkers, mechanisms, and drugs, and test those drugs at an accelerated fashion as well. Okay, I'm going to show you some. So how does it work? The first thing we do is a rapid aging microgravity protocol. I'm going to show you how that works. Then we go ahead and validate all these signatures in crew member data. I told you a little bit about that. Inspiration 4, Axiom 2, Twin study, NASA Twin study, JAXA 6, the Japanese agency as well. And then we do compound screening to try to identify hits that will serve to reverse these signatures. And then we test those in our ground analogs of microgravity. Okay. And last, we go on disease mapping. So we don't start from the disease. The last thing we do is to map these things for a particular disease and try to identify the indication that we will go after. Okay. So how does it work? We don't use animals. We don't use model organisms. We use humans and human tissues and human organoids. So we take immune organoids, and these come from tonsillectomies, and those are really mimicking what happens in the real life. You cause a flu vaccine, produce antibodies. You cause a viral, particular virus, produce T cells. It's really amazing how they mimic what happens in vivo. Again, mice don't even get the flu. So, okay, so this is much more realistic. Cardiac organoids, we take those from IPS, subject them into microgravity, and do all sorts of things, including irradiation with a good head in National Lab in NASA to mimic what happens in deep space. And then neural organoids as well. And last, peripheral blood mononuclear cells, that are subjected to this microgravity simulation. It's a facility that we have at the Buck Institute. And that's basically a rotating wall vessel that was designed by NASA to simulate microgravity on the ground. Okay. Once we have that, and just some data, it's just really cool. So 1G, that's just 1G, basically gravitational forces that are affecting us here on the ground. Compared to microgravity, we see an increase of about 50% in inflammatory age. This is a metric of inflammation only by spinning this thing for 24 hours. Okay. Now, we also see reactivation of viruses, similar to what we see in crew members. They reactivate a number of different viruses, shingles, herpesviruses, and so on. We see altered microbiome, hallmarks of aging, right? And then cellular senescence. We have the Mayo database and many other signatures of cellular senescence that are increased during microgravity treatment. And last, this is really important. Please look at this beautiful super resolution microscopy slide, where we see that in 1G, the cytoskeleton, the actin cytoskeleton is well formed, it's nicely shaped, and it has the mitochondria all sitting together very nicely and functional. What happens in 1G, that's not the case. And so what we believe, I'm going to show you, well, first of all, we are recapitulating at least half of the hallmarks of aging. Okay? What we believe it's happening, similar to what happens in aging. And this is a very new field of mechanotransduction. So there are sensors in those cells. Gravity, right? Gravitational forces are sensors. And mechanical forces will affect the way the microtubule will ultimately form. Right? And so what happens when we are subjecting these cells to microgravity, they become dysfunctional. There's a rearrangement of the cytoskeleton, of the actin cytoskeleton, and mitochondria and many other organelles will suffer. And how they suffer? Well, they start producing ROS, they start producing less ATP, a lot of different issues that mimic what happens in aging. Ultimately, what we see is systemic chronic inflammation going up, both in crew members and in our system, and also immunosenescence, a decline in immune response that goes with a number of other pathological features that I mentioned before: cardiac, neural, musculoskeletal. Okay, so here's the signature validation part of our model. We take flight crew data, we run the overlapping with our own ground analogs, and then we take large aging databases of things that happen on the ground. Okay, 1,000 immunomes that I've lead, and UK Biobank, and many others. And here, that's our target, right? That's our targets. And after doing that, well, we have, as I mentioned before, collaboration with Cornell, SpaceX, Axiom. We're planning to, hopefully, we can raise the funding, entirely own the Axiom 2 data. And this is, again, before, during, so in flight. We can sequence in flight. And after flight, data, multi-omics. Okay? This is going to cost us about $1 million. It's not that expensive, but still for 4 members, it's kind of pricey. We're trying to secure those funds. And then the aging cohorts on the ground. I mentioned a few, the 1,000 immunomes cohort, the Hillbom cohort at the UCSF. We have access to PROMISE cohort, 10,000 immunomes from UCSF, etc. And then after we do that, we take a very unbiased approach to try to combine over 150,000 compounds from different databases, Drug Bank, Links 1000. Oh, yeah, okay, thank you so much. And then FoodDB, to try to take all these compounds and ask an algorithm to pull compounds that will reverse these signatures of aging. Okay, and we have a archive, actually, if you guys are interested. So we have lead compound database. This is basically for hit identification. And what I'm showing you in the columns are the genes that will be affected by these different compounds. This is just an example of a COVID project I did before. So just putting it here as an example. But actually, we do have data now as a proof of principle that we identified a compound that we then tested on our model. This is the hit to lead. And what happens is we can reverse up to 70% of the signatures we see in aging. Okay, and you're going to recognize some of these things. You guys are in the longevity space. So all these are aging related. Erythropoietin, which counteracts tissue hypoxia, is down in our ramp system, and then it gets reversed with our compound. Things like P4 alpha, HIF1 alpha, senescence pathways that I mentioned before. We're capturing all these hallmarks of aging, reversing those signatures effectively, and we want to be able to map these things to diseases to go after as a primary indication. This came out a little bit bizarre, but bottom line, this is going to get obviously is subject to change. We're planning to start with immune aging or cardiac aging and then neural aging, but we're also going after particular disease indications based on multiple things, not just the recapitulation of what we see in our studies, but also regulatory payers, a number of other constraints and filtering that we have to do to identify the right disease to go after initially. Okay, huge longevity market is growing very rapidly with an annual growth rate of around 10%, 7 to 10%, give or take. And we just officially opened our seed round as of yesterday, or the day before, actually. So there's a 20% discount for early investors. If you're interested, reach out. If you're interested in discussing partnerships, also reach out. And that is it for now. Thanks.
So we're going to open the floor up for questions. Oh, here we go. Super cool, David. Like bring those two ambitious things together.
Thanks.
You showed like those white lines, which was like normal aging trajectory and things that go worse, and then you showed the yellow lines that were like space flight. How long does it normally take for like those yellow lines go back to baseline once astronauts are back on Earth?
Yeah, excellent question. So it's really interesting because for some phenotypes, you can actually see a regression, rejuvenation very rapidly. For some phenotypes, that doesn't happen for years. So cardiovascular it's taking a very high toll in this thing. Immune responses are much more malleable, so they get better over time. So there are, but imagine this is beautiful because as they return to Earth, there is a rejuvenation process. There are geroprotectors that are happening naturally there in these individuals, but it's variable and there's not much data.
Okay.
Yeah.
So 0.1 G bad for you, 1 G better for you. What about 2 Gs?
Yeah, I've had many investors asking the same question. I don't know if you're an investor, but it's probably not rejuvenating at all. It's actually as bad. I would assume it's as bad as micro G, because we haven't evolved into G. Basically because of that reason. We don't have data, but that's my assumption. If you're moving from a evolutionary conserved the mechanisms that you evolved with, you're probably going to get inflamed, you're going to get micro dysfunctions, loss, etc., etc. Yes.
Maybe stupid question.
There's no good question.
So moving from Earth to reach the same level of damage in the organisms, the cells, the same organs, different aspects of world in space.
I think I touched on that. Depends on the system. I probably don't have it here, but on average, there's 30-fold increase in the rates of aging. So for every year that you spend on the International Space Station, that corresponds to 30 years in the ground.
So the following question, so if you develop a molecule, how do you then validate it when people put aging over?
Yeah, awesome question. Yeah, right. So the first thing is that we tested on our models. And then this is a question for everybody in the field. How do you test aging? You have surrogates of aging, all the clocks that are kind of not perfect. There are other surrogates. There are some soft measurements that you can have, or improvements of some. Say, for example, if I change arterial elasticity, that can be changed very easily in 4 months, right? Also, velocity testing that can be done in a scale, very easy Withing scale measures that, and you can actually improve that. That's a signature of aging. Now, if you want to rejuvenate your heart and maybe reverse your hypertrophy in your left ventricle, it will take maybe 5 to 10 years. So it really depends on the endpoint that you're looking at. Yeah.
You say 30, 30.
Exactly. 34, 30. No, up to a year. That's the swing study. Kelly and Mark, Mark and Scott Kelly. Yeah.
Well, when they
I'm sorry.
By what metrics do you use?
There's a number of different metrics. It depends on. No, not at all. I'm referring mostly to pathological science, not molecular science. At the molecular level, we're just figuring out what's happening. Those lines are all physiological responses. So heart,
blood pressure.
yeah, exactly, and cognition and muscle mass, bone mass, immunosenescence to get reactivation of viruses, very similar to what you see in normal aging.
One investigated one like 9%.
When you by large, the effect of microgravity matter. Yes,
when they do get back on Earth, as you said, some of these recover quicker than others. What is the average lifespan of these astronauts? Are they like the same as us, or do they die early?
There's no data. There's no long-term data. And it's a tricky question because we're trying to access the data, and there's little data that there is. And there are all these roadblocks all over the place. I couldn't imagine how difficult it is to work with the agency, for example, right? Say an example, I want to use samples that have been stored from the Apollo era, right? They're there. You can use them and learn so much. They're considered national treasures. Okay, what are they good for? I don't know. So the data isn't available. Yeah, I think. Yes. So the question is about the power of the studies and the under low sample size that we're suffering from when it comes to astronaut data. That is true. We don't have extensive samples, and we're recruiting astronauts actually at the moment for a sun study, which is a neuroocular disorder that you get from intracranial pressure. So if you know any astronaut out there, it's very difficult to have large sample size, but we do have very full characterization of each one of these. Let's say Inspiration 4 members that went up there. We have many time points before, during, and after. We also we're collecting, right? All this. Axiom 2 is going to launch in May of next year. So we're going to try to have the data for these 4 members as well. But we have the power of doing this also in conjunction with data of humans that age on the ground. So that's the overlap that we're aiming for here to kind of understand what are the targets. But so far, we have JAXA-6 data secured, the N of 1 of NASA twin study, the Inspiration 4, and hopefully Axiom 10. Yeah.
So the basically similar to aging, similar.
Yes, there are some dissimilarities. So at the molecular level, we haven't found ourselves dissimilarities, but there are some reports out there that show an elongation of telomeres, for example, during space, which was shocking to me. I couldn't kind of make my hair around that. And the other thing that we've been seeing in some studies, which is not, yeah, kind of an obscure journal, that the epigenetic age may go down in some astronauts in microgravity. But I don't know what that means really. So yeah, so some differences, but for the most part, there are similarities. And when you look at the clinical data, it's very convincing. Yeah, I think the whole idea of changing your cytoskeleton, the acting cytoskeleton, how the cell senses by mechanotransduction. There's a whole reorganization of the cytoskeleton. We have a paper that just got submitted to Nature Medicine, and it includes all this justification of why there are these similarities between molecular similarities between aging and spaceflight. And I think it has to do with the mechanotransduction, which is a fairly new field. And there's a lot of attention being paid in the aging space of how the cell senses mechanical forces. There's a complete remodeling of the extracellular matrix, for example, in aging. And there's very low responses to mechanotransduction in older cells as opposed to in younger cells. Very similar to what we see in the organoids in microgravity.
Time for one more question.
Yeah.
The mitochondrial changes not last year when suggested that mitochondria will come step range.
Right. That's paper, cytoskeleton does not measure at all. At the moment, we're doing time series, and that's going to give us lessons. So we do 2 or 6 minute hour incubation, and 24, 48, and then you have a causal effect, and you can kind of draw those conclusions. Yeah, absolutely. Yeah. All right. Thank you so much.
Thank you.